Lab 3, Black Hole Lab. In this lab, we observe the motion of a star and use those observations to identify the forces. Unlike the previous labs where we predicted the motion of an object using initial conditions, we are essentially going backwards in this lab. We are using the object's motion to identify the initial conditions, which, in this case, is the mass of the black hole. The two models that are relevant to this lab are the gravitational force equation and Newton's second law. Newton's second law is the change in velocity divided by the change in time multiplied by the mass. This equation can then be rearranged as the change in momentum divided by the change in time. This equation calculates the net force of a system. And the other equation that is important to this lab is the gravitational force equation. This equation allows us to calculate the mass of the black hole. Since the star is in orbit around the black hole, the gravitational force on the star is the same as the gravitational force on the black hole. Since we have the initial conditions of the star, it is possible for us to calculate the net force on the star, which is the same value for the black hole. Thus, using the gravitational force equation, it is possible for us to calculate the mass of the black hole. To calculate the net force, we first calculate the change in the velocity of the star from the CSV file. These lines of code here are used to find the x and y components of the star's velocity. Then we calculate the initial and final velocity by finding the change in velocity between two time periods and then dividing that value by the change in time. Next, we find the initial and final momentum by multiplying the star's mass and the initial and final velocities. From these values, we are able to calculate the change in velocity and the change in momentum, which are delta V and delta P. From Newton's second law, we know that net force is the change in momentum over the change in time, and these lines of code here calculate the net force. These next few lines of code are used to calculate the perpendicular and parallel components of the net force. The parallel component is the magnitude of dp dt multiplied by p hat. We find p hat by dividing the initial momentum and the magnitude of the initial momentum. The change in the magnitude of the momentum is calculated by subtracting the final and initial momentum and dividing that by the change in time. Thus, we have the values we need to calculate the parallel component of the net force. The next component we need to find is the perpendicular component, which is found by subtracting the net force and the parallel component of the net force. The net force can be composed into these two components, the perpendicular and parallel, and if we add them together, we get the net force. In order to find the mass of the black hole, I use the gravitational force equation. We already have the net force, which is the value we calculated from the initial conditions of the star, and we have mass 1, which is the mass of the star. G is a constant, and R is the distance between the black hole and the star. To find R, I subtracted the position of the star and the position of the black hole. Here, I've rearranged the equation so that I've isolated mass 2 on the left side and all the other variables on the right side. The calculated mass 2 is the mass of the black hole, which came out to be 1.99 times 10 to the 34 kilograms. Here's the code when it is run. We can see all of the components of the net force. Fnet perpendicular always faces the black hole, and Fnet parallel follows the direction of motion. The net momentum and its components only differ from the net force and its components in the way that they are calculated. Numerically, they are the same values. The main difference is that dp dt doesn't affect the star's motion, while Fnet does. dp dt just tells you how the star moves. Now for our what-if question. What if the black hole was replaced by a different black hole, but none of the values from the CSV file changed? Would we be able to find the new value for the black hole? Well, since the star's motion doesn't change, and that means that the star's velocity and time also don't change. This means that dp, dt, and Fnet won't change. If none of the values change and we use the same values in the gravitational force equation to calculate the mass of the black hole, we cannot tell the difference between the masses of the black hole.